Hello and welcome back. Now in the next classification that we are going to continue in this video is laminar versus turbulent flow. Now in the last video, I'll put the link here. In the last video what we learned was viscous versus inviscid flow. Now we have to remember that viscous flow can be of two types. One is called laminar and another is called turbulent. These are the two types of viscous flows. Now suppose we know an example of viscous flow is internal flow. Internal flows are viscous dominated, they are viscous flows. So internal flow means flow inside a pipe, fully filled with pipe. Suppose we have a pipe, say circular pipe, and it is fully filled with whether air or water, whether liquid or gas. We call it internal flow. Now these are viscous dominated. Suppose this is a pipe that is filled with water, and suppose we use it faucet. Suppose faucet in front of it, and when we open the faucet by small amount so that the flow rate is small. So when the flow rate is low, when the flow rate is small, we will see, and we have experienced this, that this water flows at a small flow rate. Water flows in layer, it flows smoothly. It flows very smoothly, as it seems that this flow is made of liquid layers, small liquid layers. So this type of flow in which the fluid particles move in layers, we call it laminar flow. Layers means laminar, it flows in laminas, that's why it gets the name laminar flow. But if we increase this flow rate, if we open it more and increase the flow rate is high, what we will see is we will no longer see that smooth flow. We will no longer see that flow is smooth and made of laminas, made of layers. But what we will see is a messy, chaotic fluid motion. It is made of layers, but one layer is crossing the another, so different layers cross each other, so the fluid mixes while these fluid particles mix with each other while flowing. It's called turbulent flow. So same viscous flow, that's why the same viscous flow has been divided into two categories, laminar flow and turbulent flow. Now in case of laminar flow, what we have is the velocity of laminar flow is one dimensional. Suppose if we have if we consider this flow moving only in one direction, so its velocity will be, say, if this is x direction, if it is x-axis direction and the velocity component in this direction is taken as u, so the velocity of this one dimensional laminar flow is expressed at u I cap or I hat. It's very simple, and we see that the shear stress between the fluid and this solid wall, this shear stress is equal to mu du by dy. That means the relationship between this mean velocity, one dimensional mean velocity, and the shear stress is given by this simple relation. Mean velocity, shear stress, this is given by this simple relation called Newton's law of viscosity. We'll study it in different videos. Now there is a simple relation in case of laminar flow. Now if we talk about the turbulent flow, what happens is there is definitely, if the same flow is turbulent, there is definitely a one dimensional velocity component, but that's mean velocity component. It is something like this. It has a mean velocity component u bar. It is not smooth as laminar. It is highly chaotic motion, turbulent motion. The fluid particles mix with each other. And what happens when they mix with each other? Why they mix with each other? That's the first thing. Because there is not just this u component of the velocity. V is not just equal to u I cap, just like this. But what we have here is there are components, there are fluctuating velocity components in this case. Even it is one dimensional, but there are three-dimensional velocity fluctuations. 3D is important. 3D velocity fluctuations. When there is three-dimensional velocity fluctuation, that means velocity keep fluctuating. Even it is one-dimensional, velocity keep fluctuating along x-axis, y-axis, and z-axis, which cause that mixing of these fluid particles. And that's why we write this. And there are three more components: u prime, v prime, and w prime, where u, v, w are the velocities along x-axis, y-axis, and z-axis. X-axis, y-axis, and z-axis. U component, v component, w component, and they are, since they are fluctuating, that's why prime, prime, prime. These are the three-dimensional velocity fluctuations which keep on fluctuating around this mean value. And because of these three-dimensional velocity fluctuations, the fluid particles mix with each other, and due to this mixing, what happens? Two things happen. Or we can say one thing happen: momentum transport occurs across mean velocity. This mean velocity line, momentum these velocity fluctuations occur like this. So it keep on fluctuating, but the mean always stays the same. The mean stays the same, and these 3D velocity fluctuations keep on changing this velocity component, and because of this, momentum transport occurs across this mean component. So when this momentum transport occurs across this mean component, what happens is shear stress increases. Or we can say effective shear stress increases. So this is the same pipe. When the flow was laminar, the shear stress between the fluid and the solid wall had some value. Now if the flow rate when the flow rate was increased, flow became turbulent. Now the shear stress between the fluid and the solid wall is higher, because effective shear stress increases in turbulent flow because of this momentum transport that occurs, which occurs due to this fluctuating 3D velocity component. This is what happens in turbulent flow. So the entire velocity that we express in case of turbulent flow is like this. So this will be the difference between the laminar and the turbulent. So laminar case is simple, and it is developed using the theory alone. So we have shear stress at the wall is equal to mu d of that velocity divided by dy. Now in case of turbulent flow, let's continue with the laminar flow first. Now this u here, the velocity component here is u I cap, as I said before. Now in case of turbulent flow, what we have is velocity component is u bar I, mean component of this one-dimensional velocity, but it is added with the 3D fluctuating component. So since it is 3D fluctuating component, so we have all the three terms: u prime, v prime, w prime. So u prime will be added with this mean u, so I cap. Then there is separate v prime, j cap, and there is w prime, k cap. So this is the difference between the velocity field in case of laminar flow and the turbulent flow. So it is same, except we have 3D velocity fluctuations which result in momentum transport across the mean velocity, and which increases therefore this consequently increases the effective shear stress. That's why turbulent flows show higher shear stress than laminar flow. Now in case of laminar flow, the relationship between that shear stress and this velocity is very simple, like this. But in case of turbulent flow, since the velocities fluctuate, 3D fluctuating, complex velocity field exists. That is why there is no theoretical perfect equation given by the theory alone, just like this, that describes the relationship between the wall shear stress and the velocity field and the velocity component. And that's why in case of turbulent flows, we have to rely on semi-empirical relation, semi-empirical models or relations, or experimental data, we can say experimental data. So what are these two terms? So in case of turbulent flow, either we have to go for experimentation, use experimental data to predict something, purely experimental data, or what we have, at most what we can have, we can combine the theory and experimental data to generate some equations which are not fully developed from the theory, using the basic laws of physics, like the conservation of mass principle, conservation of energy principle, conservation of momentum principle. Those will be the equations developed purely from the theory. So that is not the case for turbulent flow. So for turbulent flow, we combine the theory and the experimental results to develop the equations. We call them semi-empirical models or semi-empirical relations. So for turbulent flow, that's why we do not have these simple theoretical relations. We have to rely on either purely on experimental data, that the data given in the form of tables, graphs, or we have to rely on equations that are not fully theoretical, but developed by the combination of theoretical part and experimental data, call them semi-empirical relations. So that's why we see turbulent flow theory is more difficult or more complex than the laminar flow theory. Now, since we talked about this internal flow in pipes, now whether a flow inside a pipe is laminar or turbulent, how do we decide that? Now we use the non-dimensional parameter that we discussed last time, which is the Reynolds number, which was defined as rho VL by mu. Now experiments show that if this we open this tap at low flow rate until this flow is laminar. So if we keep at that border line, at that bottom, at the borderline above which the flow becomes turbulent, below which the flow is laminar, if we keep it at that point, we see that below that point, if we calculate this value, if we combine these parameters and find Reynolds number, it is 2300. So if Reynolds number is lesser than or approximately equal to 2300 in case of internal flow in pipes, internal flows, if it is less than 2300, the flow will be laminar. And if the Reynolds number is greater than 4000, it is regarded as fully turbulent. So we can study it using the turbulent theory, turbulent data. If it is lesser than 2300, we use the laminar theory that we study. And if it is in between, if the Reynolds number is between 2300 to 4000, which means this value of Reynolds number gives us another flow regime. We call it a transitional flow regime. What happens is below up to 300 is purely laminar and above 4000 is purely turbulent. In between it is transforming, and it is transforming itself from being laminar to being turbulent, and that is called, it is transitioning between laminar and turbulent. That's why we call it transitional flow. So it is transitional flow between 2300 and 4000. The equations will be totally different for laminar flow, theoretical relations mostly, and the data, that relations that we use in turbulent flow will be different, and the relations equation that we use in the transitional region will also be different, because flow behavior is totally different. So this was the another classification of fluid flow, that's laminar versus turbulent flow, and the importance of Reynolds number in this as well. And I gave the critical value of the Reynolds number for internal flow, which is less than 2300 for laminar, greater than 4000 for turbulent, and in between it will be transitional flow. So that will be all for this topic, laminar versus turbulent flow. In the next video, we are going to start this compressible versus incompressible flow field. Thank you.